Okay, so here's H-23. So we're going to do something called linear approximation, which also means tangent line approximation. And so it's based off of this fact. For x values super close to x equals a, okay, where a is some number, f of x is approximately L of x. Okay, L of x is the linear approximation because L of x is the tangent line. It's actually the tangent line, you'll see in a minute. So f of x is approximately L of x, where L of x is equal to f of a, there's that number, a, plus f prime of a times x minus a. And guys, if you notice from the past, this is the formula for the equation of a tangent line, 2f at x equals a. Okay, so let me show you basically, it is a picture what this is saying. Okay, so here we have, I'm sorry for the blurriness, here we have this function f, and let's compare 4. Okay, so 4 is the point of tangency. So at 4, f, all right, so let's say, so if this is the tangent line, if the tangent line is y equals 1/2 x plus 10, okay, then what that is saying is that L of x is equal to 1/2 x plus 10. All right, if we're thinking of the tangent line in terms of linear approximation. And if you look right at the point of tangency, right at that point, you could see that f of 4 is exactly equal to if you plugged 4 into the tangent line. But if you look at, so this lower dot is a point on f at 4.1. So this lower dot is f of 4.1. But the one up above, that is L of 4.1 because we're plugging 4.1 into the tangent line equation. And you could see that they're not the same. F of 4.1 is not equal to L of 4.1, but they're close. Okay, they are close. So so for any number that's, so since 4.1 is close to 4, the function f is approximately, it's about the same as the tangent line. The y values of f are about the y values of the tangent line. So f of 4.1 is approximately what you'd get if you plugged 4.1 into the tangent line, okay, which is L of x here. Okay, so that's just a little example that I gave people last year. And so that's what it looks like visually. Now let's read this problem. Given that y of 1 equals 7, y prime of 1 equals -2, and y double prime of 1 equals 9, use linear approximation, which is the same as tangent line approximation, to estimate the value of y of 1.3. Guys, notice 1.3 is pretty close to 1. So they're giving us the y value at 1, they're giving us the y prime value at 1, and they're giving us the y double prime value at 1. And they're asking us to use linear approximation or tangent line approximation to estimate the value of y of 1.3. And 1.3 is close to 1. So that means we could use the tangent line equation at 1 to estimate the function value of 1.3. So now this part is going to require some more of a demonstration from me. Is this value an overestimate or underestimate? Explain. And I like to point usually to the words as I'm explaining, but it keeps focusing in and out the camera when I do that. So that's why I'm not that much. Okay, guys, whether the tangent line is giving you an over or under approximation is going to depend on concavity at the point of tangency. So I gave you some examples here. Here's two concave up situations. You could have the function is increasing in concave up or decreasing in concave up. Guys, the increasing or decreasing doesn't matter, but since the function is concave up, it's happening that the tangent line is underneath, the y values of the tangent line are underneath the y values of the function. And same thing over here. Since f is concave up, the y values of the tangent line are underneath the y values of the function. Then, for the other cases, increasing, decreasing, it doesn't really matter as long as the function is concave down. The y values of the tangent line are over the y values of the function. Okay, and same thing here. All right, so we've got two facts here. If f is concave up, and guys, it's, you might be thinking, do I have to memorize all these facts? I mean, you could, but it's easier to memorize if you could visualize, for sure. When I have forgotten these in the past, I have just like sketched something. Like you sketch, if you can't remember concave up or concave down, which gives an over, which gives an under approximation, sketch a part of a graph that's concave up. Do a tangent line, see if it's over or under. Sketch a part of a graph that's concave down. Do a tangent line, is it over or under, okay? So if f is concave up, then the tangent line gives an under approximation. Okay. So you could think f is up. So f is up, so the tangent line's under. F is up, so the tangent line's under. If f is concave down, then the tangent line gives what kind of approximation? Over. Gives an over approximation. So if f is down, then the tangent line is over or above. If f is down, then the tangent line is over or above. Okay, so when we explain why we have an over or under estimate, we're going to have to use concavity. And it's the second derivative that's going to tell us about concavity. That was a lot of explaining. Okay, so we're given all of this, blah, blah, blah. So if we're going to use linear approximation, we've got to go L of x equals, instead of f of a, we've got y of 1. Y of 1 plus y prime of 1, x minus 1. So L of x is 7 minus 2, x minus 1. So L of 1.3, 7 minus 2, 1.3 minus 1, and I already did this, equals 6.4. So f of 1.3 is approximately 6.4. Okay, now is this an over or underestimate? Explain. Okay. Well, guys, y double prime of 1 being 9, this right here is telling us that y is concave up because y double prime is greater than 0. That's what that's telling us. Okay, so this, if y is concave up, okay, if y is up, then the tangent line is under. So it's going to be an under approximation since y of x is concave up at x equals 1. All right, but then you have to keep asking why. So, and it's, and your explanation should go back to Susan's table. Okay, so if you're looking at Susan's table, when would y be concave up? It would be when y double prime is positive. Okay, because y double prime of 1 is greater than 0. Okay, so we got under approximation because concave up, because y double prime greater than 0. Okay, so that's how your explanations should go for this over or under approximation. Okay, let me be fast on this one. So the quantity of a substance can be modeled by this function P of t that satisfies the differential equation right there. Guys, a differential equation is just an equation involving a derivative. This means an equation involving a derivative. All right, that's what a differential equation is. So it's involving this derivative of p, dp dt. That's the same as p prime. This differential equation. One point on this function is p of 0 equals 480. Based on this model, use a linear approximation to the graph of p at t equals 0 to estimate the quantity of the substance at t equals negative 0.1. Negative 0.1 is close to 0. Okay, so for values super close to 0, the function itself, the function values themselves are going to be approximately the tangent line values. Okay, so I go L of t this time. So L of t is equal to p of 0 plus p prime of 0 t minus 0. Okay, so it's t instead of x. Okay, so L of t is equal to, so p of 0 is 480 plus p prime of 0. Well, guys, 0 is going in for t, and if I look at this function p prime, or dp dt, I don't see any t's. So it's not like I can plug 0 in for t, but I do see p here. So let me off to the side. All right, so this is an aside. dp dt evaluated at the point 0,480 is equal to, all right, now what goes in for P? This is T, this is P. Okay, P is the output. 480 minus 300 equals negative 1 over 60. Oh, it's negative 3, that's nice. Shoot. Okay, so negative 3, and then that's just t. So this is 480 minus 3t. All right, so that's the tangent line. So that's going to give us, that's our tangent line approximation. Okay, now we want, so L of negative 0.1 is equal to 480 minus 3 negative 0. Oh. Okay, I hope I'm doing this right. I think I am. Let me think. Sorry, guys. It's just really close to... No, that makes sense. That makes sense. Okay. So 480.3. All right, so we've got that P of negative 0.1 is approximately 480.3. And if you wanted to know if it was an over or under estimate, you would have to take the derivative again of this to get the second derivative. And, you know, and then see if the second derivative is positive or negative at 0, 480. Okay, guys, sorry, that was a lot of explanation, but this is a very visual situation, so I wanted to make sure that was clear. And if it's not, please let me know.